So if I had when we were dealing with quadratics, if I had x squared plus 9x plus 20, and I said factor that, and that was the goal, was just to factor it, you would write the factors down, and you would, or write the parentheses down. First of all, you look for something you could pull out. There's nothing there. Split up the x's, and then you would ask yourself, factors of 20 did add up to 9, and that would be, yep, 4 and 5, 5 and 4, either direction. Positive 9, so they're both positive. Does that all make sense to you? And then you would go to the next problem. That's what you've been doing. In 4, only it wasn't quadratics, it was polynomial. So you use synthetic division to come up with these guys. And then when you were done writing all the factors, you'd stop. Well, today, we're just taking it one step further. And that is, we're going to ask you to solve this. So we're going to say equals 0. And if it's not equal to 0, you get everything on one side where your leading term is positive and set it equal to 0. And then go about the process of factoring that you learned in 4.4. And so in this case, we would say equals 0. And so we would continue and say x is equal to -4 and -5. That's really a small step. You've done this before with quadratics, right? So today we are going to take it one step further from the factoring and use the factors to determine the zeros of the polynomial. And it's just like it was with quadratics. These are places, these are x values for which this graph hits the x-axis. Okay? A little more to it than just that. Otherwise, we'd be done with the lecture. So, it has to do, this extra stuff has to do with the behavior of the graph. Let's pretend, it's really difficult to make up a polynomial that this will work with. It'd take me a long time. But let's pretend that you had a polynomial, an x to the 4th polynomial, and it was plus blah, blah, blah. This is what I'm dealing with, and it equals 0. And let's say that your factors turned out to be x minus 3 and x plus 2 and x plus 2 and x minus 3. Let's say you did all the synthetic division, did everything out, and this is what turned out to be the factors. Then what this really is here is x minus 3 squared, Sam, times x plus 2 squared. Which means that the zeros are 3 and -2, but they both showed up twice. So when you get to here, or even here, right here, you have this equal to 0, and you say, okay, I've got a 3 and a -2, oh, -2 again, and, oh, and a 3 again. That comes from this, if you summarize a little bit like this. If this shows up twice, that means that x equals 3, and this is how we write it. It's a subscript, not a superscript like an exponent. It's a subscript. And you can either put just how many times it shows up, which is 2, or you can put M2. I've seen it both ways. I always write M2 to remind myself what it is. This stands for multiplicity. That's what the M stands for, multiplicity 2. And what it means is that 3 is a 0 of this polynomial twice. It's important to understand what these multiplicities do. So give me a few minutes to unroll this. So when we answer this question, you would say x equals 3 multiplicity 2, or let me tell you how they want it, big ideas math. 3, 3, 2, 2, -2 actually. For me and the writing, and when you take a test, I would prefer it, you could do this, but I would prefer to know that you know that that means, oh, it showed up twice. I like this better, but I think big ideas want you to do this.
Why isn't the 3 and the -3 or -3 also? If they're, oh wait.
They're both x minus 3. Okay.
Nice.
That's okay. It's a good question. Are you clear on this expression and this one being the same thing and where we got them from? Now, you need to understand the behavior of the graph with these multiplicities. And I'm going to give it to you in general. If the multiplicity number is even, as it is in both cases here. If it is even, and notice this x to the 4th thing that I wrote here. This is a 4th degree polynomial with a positive leading coefficient, meaning it will start high and end high. Remember that from 4.1? And as it starts high and then finally ends high, on its way through, it's going to hit 3 and it's going to hit -2, but it's going to bounce off them because the multiplicity is even. So without knowing the heights of all of these things, I can tell you this for sure, without ever graphing this thing, that if these were the factors of it, then at -3 it will bounce off. No, sorry, that's a -2. At -2 it will bounce off, and at +3 it will bounce off, meaning it will come from above because it starts high, and when it encounters the 2, it won't go through. It'll bounce off, it'll come up, and when it goes down here to encounter 3 on the x-axis, it will also bounce off. Don't know how high this goes, but I can guarantee that it's going to look like this, where it hits the x-axis, and I'm going to guarantee it's going to go high and high because of this stipulation we learned in Form 1. Even positive leading coefficient. If this had been the factorization of that one, then it would have done this and bounced off the x going down. It would just kisses it and bounces off, does not go through. Yes?
But isn't it supposed to hit 3 twice and hit -2 twice?
No, it's just saying that it will encounter the x-axis at 3. But because the 3 shows up twice in the solving of this, the encounter will be a bouncing encounter rather than a going through encounter. That's what the multiplicity even tells you.
2, it means it's bouncing off instead of.
Because of the multiplicity 2 on the -2, it'll bounce off there too. Okay. Now, let's pretend, so that I don't have to erase a whole bunch of stuff. Let's pretend that this thing started out as a positive 5th degree polynomial, and I had these as factors. By the way, and I'm not supposed to tell you this yet because it's supposed to be in a whole nother section, but I'm going to tell you anyway. If you have a 5th degree polynomial, you will get 5 zeros. Some of which may be repeated, as in the case we're discussing here, some of which may be imaginary. But there will be 5. Okay, so now what I have is this. Do you agree? I also have this. Multiplicity 3 on that one, which is odd. So I have a 3, which showed up an odd number of times, and a -2, which showed up an even number of times. When the graph encounters the -2, it will bounce off, because that's what the even tells us. But the odd one, it will go through, but not easily. You will not find the words I'm about to use in a book, but I think you'll understand. I hope you do. So this would be like this. And what that means is, because this is an odd degree, this is a positive leading coefficient, it will, anybody know?
Go up and then go down.
It will start,
High.
not when this is positive, it will start low and end high. Okay? And it will have this behavior when it runs into the x-axis. Watch. We've got these two different zeros, one at -2 and the other one at 3. And here's what's going to happen. It's going to start from down here on the other side of -2. But because to -2 showed up an even number of times, as it comes up and hits this one, it will bounce off because the multiplicity is even. But then when it comes up over here and encounters the 3, it's going to do what, you won't see this in the book, what I call hedging. It's like if you were this guy tracing this, it's tracing as you go by, and you say, oh, no, here comes a 3, I don't want to go, I don't want to. Okay, I will. It does not go slamming through it with no fear, I guess. It comes up and it hedges on its way. It bends right here. It hits only at 3. I know it looks like it rides a little while flat like that, but it doesn't. It just stays closer to the x-axis longer. But it only hits it at 3. But it will go through if it's odd. But it will have this little hedging behavior right here when it encounters the x-axis. Now, if you had, and I'm not going to come up with an equation for it, but if you had something like, I'm going to erase this so you don't think one has to do with the other. I'm just going to erase this. Let's say you did this isn't actually going to happen to you today. I'm just telling you what to expect. I'm going to erase this too. Let's say we got through with the factoring, the synthetic division. We got all our factors. We wrote down the factors. We wrote down all the zeros, and this was our list. We had x equals 3, -1, multiplicity This will never happen, but just stay with me and don't freak out. Multiplicity 8, just hang in there, comma, and let's say we had 6 multiplicity 9. That's a heck of a polynomial. That's got 17, that's got 8, that's an 18-degree polynomial. But I just want to show you what happens. It's the odd and the even that matter, but the higher these numbers, the more something I'm about to show you happens. So what you would do, if we got a list like this, well, you won't, but I just want to show you what's going to happen. If we had a negative, we have a -1, that's one of our markers, a 3, and a 6, that's where it's going to encounter the x-axis. Since this is an 18-degree polynomial, I'm going to assume that the leading coefficient was positive, so I have this, like that. And these are the zeros we came up with. It's going to start high and end high. Can you see that? This is even degree, positive leading coefficient. You with me? So it's going to start here, but when it encounters the 1, because this is even, it's going to come down like this, and it's going to appear to ride on the x-axis quite a long time. And you're thinking, all these points are zeros. No, they aren't. It just stays closer to the x-axis longer. It hits it right here and then stays really close to it a long time. How do I know it's a long time? Because that's a larger even number. It doesn't just bounce off, but it does only hit it in one place. And then as it comes over to the 3, it's going to come up like this. And as it comes over to the 3, it'll go slamming right through. Because not only is that a multiplicity odd, it's multiplicity 1. And it just goes right through when it's a 1. It's going to go through because it's odd, but it's going to go right through and not hedge at all because it's the smallest odd number. You know what I'm saying? And then when it encounters this 6, which is multiplicity odd, it will come down like this, will come back up, and it will appear to ride a long time and then take off. But it really only encounters the 6 in one place. It's just that these other points are really close to 0. Really tight, but you can't tell it is because of the fatness of your lead or your marker or whatever. But it just hovers near that longer because 9 is larger odd. Still a hedging behavior, just hedges longer. This is still a bouncing behavior. It just bounces. It appears to ride longer before it bounces off. Anytime you have just one multiplicity, it'll go slamming right through at that point. Do you understand this behavior? Okay. You will have to read some graphs. And I've got a feeling that it's only going to be 3s and 5s. But if it's a 5, a multiplicity 3 will go like this. And it'll head on up, pretend to hedge right there. A 5 will ride just a bit longer. You'll be able to tell that's a little bit more than 3 because this will be a little longer than it was with 3. But it'll still be a hedging behavior. Okay. When you do it on Big Ideas Math, if you're doing it on that, it's going to be very clear which one to choose. Just remember that odd ones go through and hedge a bit if they're not 1. And even ones bounce and may hedge a bit the larger they are. But they'll bounce off. Go back up. Okay, that's an awful lot of math right there. Now let's actually do some problems. Okay, look at example 2. It says f of x equals -2x squared plus 16x, let's see. F of x equals negative, what was it? 2x squared?
2x to the 4.
Oh, 2x to the 4.
Plus 16x squared minus 32.
Minus 32. Okay. Remember I told you if you're trying to find the zeros of a function, you should have your leading term be positive? I still stick to that. I still believe that's true. It's going to be easier for you to handle if it's positive. So if we're trying to find the zeros of this, what we do is we let this be 0. And we could run a negative through this to change all the signs, or we could pretend we're taking all of these over here and put the 0 on the other side. What I'm saying is all these signs will change if I want this to be positive. Does that make sense to you? Let's do that, but let's not forget this was negative at the beginning, because if we're going to look at the graph, this thing's going to start low and end low. But we can still find the zeros of this graph if we apply what I taught you to make this positive. Find where the zeros are. But the shape of the graph will still depend on this negative. Okay? So we're going to have 2x to the 4th minus 16x squared plus 32. Now let's see if we can handle that by doing what you learned in 4.4, which is to factor. What's the first thing you should do when you factor?
Divide by 2.
Pull out a 2, right? Divide by 2 is good words. Those are good words. Take out a 2, what's left?
X 4.
minus 18x squared.
Minus what?
8.
I thought I heard an 18. That's 8.
Plus 16.
And then we should attempt to factor what's left, but that's a fourth degree. However, it is
Quadratic-ish.
oh yeah, excellent. It is quadratic-ish, which means we can use our quadratic processes. Split that up. What factors of 16 add up to 8? Both negative?
Yes.
Because I need a negative 8? And both differences of 2 squares. This is a difference of squares, so is this, right? So this thing right here factors into x minus 2x plus 2, conjugate pair, and x minus 2x plus 2. So now you can see possibly the way that you could get repeated factors. That's equal to 0. Each one of these factors gets their shot at being 0. This one will never be 0, so we can ignore it. This one will be 0 if x is 2. Oh, same thing there. See what I'm doing? Comma. This one will be 0 if x is negative 2. In there. Now we have to come back to the way it was presented. This thing's going to start low and end low because of that negative. We found the zeros by not having that be negative. A lot easier to handle when that was positive because you're looking for zeros. But now we come back to look at the behavior of the graph. It's going to bounce off at negative 2 and 2, but it's going to bounce off from below. Like this. Here's your negative 2, there's your 2. And because this was negative the way it was presented, the shape of the graph will have a zeros here, but it will come from below, look like that. Did you follow that? We still have to be true to the way it was presented. But we can change all of these signs in order to find the zeros, but then we're going to come back and say, how's that thing really shaped? You look at the original. And if you look at your, on page 190, that is the shape that it has. They also found the minimum. You can do that by graphing so that you get a really accurate graph. Remember we had that section on graphing accurately? Wouldn't hurt to graph it and see. That's also verification that it bounces off the negative 2 and 2. Every time I get to this part, I have this debate with myself right up until the moment I look at it when I'm going to actually show it to you, and I think I will, because there's a test question, you might as well get it. I might make it a bonus so you can get the bonus part of it. Here's the deal next. It's called the rational root theorem. And you remember that if you have a polynomial of degree 3 or higher, but it's not quadratic-ish, your method for factoring is synthetic division. Let me try that again. Will you listen to me now? Pay attention and listen to what I'm saying. This was a specially designed problem so that the 4th degree polynomial that we dealt with was quadratic-ish. Not only was it quadratic-ish, it was factorable. That doesn't happen all that often. In this chapter, we are trying to factor things of higher degree than 2. We spent a whole chapter on quadratics. Now we're taking things of higher degree than 2. And the way you have learned to factor up to this point in section 4.4 yesterday is to consider it and use synthetic division to bust it down from a 4th degree to a 3rd. And then use synthetic division again to bust it down from a 3rd to a quadratic. And then use quadratic methods on that. Do you understand what I'm saying? Mm-hmm. Question is, what the heck do you put in the box if they don't tell you? You've always been told what to put in the box in one way or another. They either gave you a factor or they gave you a number. They said, here's a 0. Now, use it to depress it on down. Remember, if you're looking for factors, the remainder has to be 0. So you can't just choose anything you want. You have to choose zeros of the function. But if that's what you're hunting for, how the heck do you find the zeros? Because it's the zeros that go in the box. And yet what we're trying to do in this section is find the zeros. That's a catch-22. Supposed to find the zeros by using synthetic division, but I need to know the zeros to know what to put in the box. So somebody came up with a thing called the rational root theorem. The reason that I don't like it is because it's extremely cumbersome, and if you did not have graphing calculators, it would be a very useful thing. So I'm going to be like your parents and wax the old days again. In the old days, when I was going to school, the best tool that we had, and they were expensive, was one of those little TI scientific calculators with just a small screen that would do things like trigonometry and exponents and stuff like that. There's no graphing. And when there was no graphing, we had to come up with another method for trying to figure out what goes in the box for synthetic division. And it's called this theorem. I'll show you how it goes. We're going to do it with an example. We're going to have x. Somebody read me example 3's equation, please.
X cubed minus 8x cubed plus 11x
Sorry.
plus 11x plus 20.
First of all, notice it's not quadratic, so you can't use quadratic things, quadratic methods. Notice also that if we are going to use synthetic division, nothing's missing. You should always notice that right off the bat so that you don't forget your zeros. But this is a 3, 2, 1 constant. We're good. And it's equal to 0. And we're looking for x values that make this 0, but we can't use quadratic methods. What we could do is use synthetic division to depress this from a cube to a square or a quadratic, and then use quadratic methods on that, knowing one of the zeros. But what the heck's the first 0? Here's what used to happen when I was your age, sitting in that desk, trying to learn this stuff. The rational root theorem says this. You take the factors, the things that all the things that multiply that go into 20, the factors of 20, over the factors of 1. So it's the back end factors over the front end factors, like this. 20's factors, this is how I do it. This is how I was taught to do it before. The factors of 20 are, actually I'm not going to write equals. 1 and 20. I put them separate like that so that I can go to the next one. I know 2 will go into it, so I put it next so that it'll end up in order, is what I'm saying. Put a 2 next, and then I say 2. So I put that over here with a 10 so that these two go together. Are you with me? See how I'm building the list, but it'll be in order when I'm done? Comma. 3 doesn't go into it. 4 does. So I write that down, and over here I write how many times 4 goes into it. 5 goes into it, but I've already mentioned it, so my list is complete. Do you see this? Everybody clear on how we found those? Okay. Now we find factors of this one. Well, that's nice and easy. It is 1. And what we do is we take factors of the back end, 20, over factors of the front end, plus or minus every time. So we go 1 over 1. I'm going to do this for the sake, I'm going to pretend this was 2. Just go with me on this because it's a lot better if this is something other than 1. I'm going to change this. I'm changing the problem, so it's not going to turn out the way it did in the book. Just stay with me. If that were a 2, then I would have a 1 and a 2 here. So what we do is we take, and you have to stay organized to get your whole list complete. We take these factors here, and one at a time put them over these factors. So I'm going to take all of these and put them over 1. But that's just these. Because they're all going over 1, right? So I'm going to have plus or minus 1, because you have to put plus or minus in front of everything. So this is 1 over 1 plus or minus. 2 over 1 plus or minus. 4, 5, 10, 20. And then I have to put each one of these things over 2 to continue my list. So it's plus or minus 1/2. That's this one over this 2. Plus or minus 1, but I already mentioned it, so I'm not going to. This one over this one is plus or minus 1. I've already got it. I'm not going to list it. 4 over 2 is 2. I've already got that one. See it? 5 over 2 I don't have. 10 over 2, I have that. See what I'm doing? 20 over 2, I have that. So my list is done. You're going, okay, that's an interesting pattern, an interesting thing to have to do. Guess what? This is a list of possible things to put in the box. So when I was sitting in your seat, we would have to try all of these, not just 1, 2, 3, 4, 5, 6, 7, 8, 16 possibilities until we went through the synthetic division, put one of these 16 numbers in the box until we got a remainder of 0. Then I would know I had busted it from a cube down to a quadratic. It was horrible. We spent all day trying to find it. scrubbing our papers clean so that we didn't have to use more paper. We would be okay to use more paper, but it was just a mess. Sometimes a problem would take 2 or 3 pages if you didn't erase. I mean, you could try this one and it's opposite. Try this one and it's opposite. Try this one and it's opposite. You might not hit it till you got to here. Because you had no idea which one of these was going to work. And let me tell you the worst of it. You are aware, I think, that you can have irrational things like -2 plus or minus the square root of 18 over, well, not 18, but 19 over 4. You can have stuff like that the quadratic gives you, and they're irrational. They're not among this list. So what happened to us sometimes when we were doing this is we would try every dang one of these 16, didn't get a hit, didn't get a 0 remainder, so we wondered, did I make a mistake? So we went through and studied them all again to make sure we didn't make a mistake. And when we had convinced ourselves that none of these worked, all we had discovered was that this thing doesn't have any rational roots. We still had to go hunting for the ones that were irrational. It was horrible. You still need to be able to generate a list of possible rational roots. You still have to use this method on one of the problems on the test. They will ask you to generate this list on the stupid dang ISAT as well. Now I've got myself recorded saying it's stupid, and it is. Anyway, they will have you generate this because they still want you to function as though you don't have those powerful tools on your desk. And it drives me absolutely nuts. But I have to teach it to you because then you will be tested on it. The test question I have for you from this chapter that has to do with that, generating that list, I will make it a bonus if you can do it.
So all you have to do is just generate the list.
What?
All you have to do is just generate the list.
Yeah. Just generate the list. Now, what they want you to do, this is what kills me. Even in the book, they say this. They say, okay, generate the list. Now, graph it and figure out which one of these best fits the bill. Why don't you just graph it first? You know, why don't you graph it first and get the zeros? Why do you have to generate this stupid list and then use that tool after you've generated the archaic list? Makes me nuts. I'm going to show you something now in your calculators that you are going to love, and you're going to be so mad at me that I didn't show you earlier. That was a reason, because when you're dealing with quadratics, you need to learn the algebraic methods. But I'll show you something really cool about your calculator. So I guess I better can you all see that? I think the people on us, can you all see this? Yes, no? Okay. I need to make sure the people on the screen can see it too. Okay. And I accept that you're going to be mad at me, but you're going to be grateful that I'm showing you at this point. Maybe you think, I don't know this before. So that means that those of you that are making up the test, now you've got this little tool you can use to check your work. Okay, so what we're going to do is take this very same equation, and I know it's hidden behind the T, but well, these people up there can see it, but it's the same one we were talking about in example 3. So what I want you to do is to put that in your y equals screen, and so you were going to graph it to look for the zeros. No, actually, I don't want you to do that. You remember, well, don't touch your calculators for a minute. I'm going to put this in here and show you what you would normally do with what you know right now. And then I'm going to show you a better way. I think I have that right. So I'm going to go to a standard screen since there's no context. That's all you get. It's a cubed polynomial with a positive leading coefficient, which is supposed to start low and end high, right? So I suspect that this thing comes from down below, goes up here, and then up here somewhere it comes around, turns around, and goes back up. We can't even see it. That's what I'm suspecting. Because of the way this thing is leaning, I'm thinking that's the come below branch. Okay? But what's cool about this is it's very clear. Of the 16 possibilities we generated, which one I should choose? -1. So we go second calc a value at -1 just to verify it's not -1.02 or something. Uh-oh. It's not -1. I'm going to have to go find the rest of it. See how that turned out to be -1.3?
Plugged it in wrong.
Yeah,
Oh, did I?
think you put it in.
Oh, Oh, good. What's it supposed to be?
2x.
Oh, 2 in the front?
Yeah.
Insert a 2, okay.
And then minus 8.
Where did I get the rest of that crap? 8 plus 11 plus 20. I guess I just can't see. All right, let's try it again. Oh, still looks like -1. Still can't see the rest of it. Let's try it again. Calculate a value at -1. Well, crap. Did I still get it wrong? No, I'm talking about example 3, people.
Yeah.
Well, it's x cubed. It's not 2x cubed.
But on the board, which column you were going to grab one?
Oh, I changed it to a 2. I wanted to show you how to generate the list.
Oh, so the list is.
The list is really only this because it was only over 1. I know you can't see that, but it only stops at 20 because it was only over 1. So let me. Why does it still not give me that? It's x cubed. Oh, because I had a 2 in front of it. 8x squared, 11x, all positives except for the 8. Okay, let's try it again. Sorry, screw this up. Oh, look, it's showing them all. And it looks like they're all 3 real. Remember I told you if it was a cubed polynomial, you should have 3 zeros. They're all real because they all hit the x-axis. It's pretty clear that, let's see if -1 actually is a 0 now. Calculate a value at -1. Oh, hallelujah. What does that next one look like? 1, 2, 3, 4. Calculate a value at 4. Oh, there's another one. The other one looks like it's 5. Calculate a 0 at 5. Oh. Not only did we figure out which ones of this list, and by the way, they're all there. -1, 4, 5. They're all here. Not only do we figure out which ones, we found them all. We're done. You just write down -1, 4, 5, and move on to the next problem. But if it turns out that they are not all nice and neat whole numbers or fractions, then you're going to have to go further with your synthetic division because you're going to have to apply the quadratic formula. But here's what I wanted to show you about your calculator that's so cool. I want you to, this time I want you to get your calculator and work with me. Can you all see that? Yeah? Okay. Go to the apps key. Go find that one of your favorite ones that solves simultaneous equations, which is alpha 8 for P. We want to find the polysomalt. Polysomalt 2 is what mine's called. Yours might just be polysomalt. This time, after we go through Texas Instruments, we're not going to choose the simultaneous equation solver. We're going to use the polyroot finder. That's short for polynomial zero finder. Finds them all at once instead of finding them one at a time like we just did on the graph. So you choose that, and this means the order, means the degree. The degree of the polynomial, it's a 3, so we go over to 3. Choose real. I know you're thinking, oh, but I want to find the imaginary ones too. It's going to cause you problems if you do. Don't do that. Just real. And then these things that are in these little loops down here, what's happened is in the programming of this app, those little things down here have become these buttons. So after you've chosen the order and what kind of solutions you want, you choose next, which is really the graph key. See what I mean? It becomes part of the solution. Okay, so we go next. And now it wants 4 things. Guess what? The coefficients of your cubed function. The coefficients. So in our case, from example 3, we would type in a 1. Enter. -8. Enter. 11. Enter. And 20. Enter. This will take you back to the main menu. This will, I don't know, this will clear everything. I don't know what this is, but we want to solve. So hit solve. Voila. Those are the 3 zeros we found from the graph. I know. Now you want to kick me, right?
Yeah.
Because you could have solved a lot of your quadratics this way, quickly, without having to go to the graph. Okay, and since they are all unique, meaning they all only show up once, we expect a graph like that. Like that. That. Now, come on. Wait. That. It's going to go slamming through in each case. No hedging, no bouncing, because they all showed up once. You all with me?
Yep.
Okay, now let's go on and do another one, and let's use this tool instead of generate that crazy list. Look at example 4. I want you to notice how lucky you are that I am not only allowing you to, but encouraging you to use your calculator. Look at example 4, at the mess. The very first thing they do is they take out polynomials, it's a fourth degree, and they generate all the possible values using the rational root in them. Look at how many there are. See that list?
Yeah.
They take the time to generate that list. And then it says, choose a reasonable value above from the graph. Why do we go to the graph first? Or better yet, the Polynomial finder. Because you have these wonderful tools, we're going to use them. So go to your apps key. Well, I have to go to my apps key because I have to go back to it. You might already be there. Always the Molt, Texas Instruments, Polynomial Finder. This is a fourth degree polynomial now, so I have to scoot it over to 4. Go to next, and now we're going to plunk in the coefficients, which are presented right underneath the word example 4. So it's going to be 10, negative 11. And by the way, if there are any zeros, you have to put zeros in where they belong to. You still have to build in zeros that are missing. We've got a fourth, we've got a cube, we've got a squared term, negative 42. That's 7, and a 12. So they are all there, but if there's one missing, you have to put a 0 in for its coefficient. Now solve. And here's what you need to notice. Are you with me? Are you looking at this? Because these decimals go on without developing any sort of a pattern or a repeat, you know that this one and this one are irrational, which means you can't report these this way. Big idea is math won't take it, I won't take it. Yes? With this on the bottom, with this on the top, and then these, it doesn't matter. It's just a list of zeros. It doesn't matter how they show up. Well, what I want you to notice is these two are irrational because their decimals are erratic. These two are nice and rational because their decimals truncate. They stop. So here's what you know, folks. You need to listen to this next part because this is where the skills of synthetic division and pulling this all together are going to be helpful to you. We will not accept these two values in that form. Not taking them. You're going to have to find the quadratic solutions that produce these irrationals by using synthetic division to depress the fourth degree that we were given down to a cube using one of these, and the cube down to a quadratic using the other one of these nice ones, and then use the quadratic formula to get these two in the proper form. But what we've discovered is a slick, quick way of finding the zeros to put in the box so that we can proceed. But we only found 2 nice ones. The other 2, since it's a fourth degree polynomial, the other 2, we've got to find with the quadratic formula, depressing, and applying the quadratic formula. Whew, boy, that's a lot of stuff. So here's how we proceed on this one. Start with the original polynomial, but we're going to start with synthetic division because, and I'm going to pull this back for just a minute, we're going to put negative 0.5 in the box and then 0.6, or 0.6 and then negative 0.5. It doesn't matter, but you need to put these guys in the box to get it down to where you can find these ones in proper form. Okay. So, can somebody give me the coefficients of that fourth degree again? I don't want the x's. Just give me the coefficients. 10? Negative?
11.
What?
Negative 11.
Thank you.
Negative 42.
42?
7.
7?
And 12.
12. Okay, what are we going to put in the box here?
0.5.
Negative 4.
Negative 0.5. Let's start with that. And you can use a decimal or you can write negative 1/2, whatever you like best. I usually like fractions better, but we'll go. We'll do this with them. And then we do the synthetic. It was negative 0.5. Are you ready?
Yeah.
Okay. 10? What's half of 10? That's what we're really doing. That's a half. What's half of 10? 5, but it's negative. Negative 11 and negative 5 is?
Negative 16.
Negative 16. What's half of 16?
Negative
8, but we changed the sign because it's negative half of 16. It's negative, negative. With me? Are you with me here? 8. Add those. What do you get?
36. Negative 36. 50.
Whoa.
It's negative 36.
That's what I'm thinking.
Oh, yeah.
Negative 34. You might want to do the arithmetic on your calculator so you don't make mistakes here. Okay, because we expect a 0 out of this. What's half of 34?
17.
17. Positive or negative? Positive. Okay, what's 17 and 7?
24.
24. What's half of 24?
12.
But it's negative because it's negative times a positive. Happy day. We did it right. But we're still not ready to apply the quadratic formula because what we have now is a cube. So we do it again. What do we put in the box?
0.6.
0.6. Now you're going to need your calculator probably.
Oh,
We use the 0.6 here. Bring down the 10. 0.6 of 10 is 6. And it's positive. So I get 10 again. Negative 10. Are you with me?
Now it's negative 6.
Yeah, now it's this times this is negative 6. And I get negative 40. Now what's 0.6 of 40? I'll bet it's negative 24.
Negative 24. Wow.
Now we have busted it down to this quadratic. That's what we have now is this quadratic. And we work on that using quadratic methods. First of all, I'm going to take out a 10. Leaves me with what?
X squared minus X.
And then you would look at that and say, can I factor that? Because I want to find the zeros of this. Can I factor that? Factors of 4 that subtract to be 1, there aren't any. Because 4 and 1 subtracts to be 3, and 2 and 2 subtracts to be 0, neither of which is 1, which means your only option is quadratic formula. But you knew that because the other two zeros were irrational. You knew you'd have to use the quadratic formula on this because we're searching for these two in proper form and they are irrational, which means that thing's not going to factor. We already knew we were going to be faced with it, so considering factoring really isn't something we should be doing. And I'm going to use the quadratic on this, not the 10, just this. That makes my numbers much smaller. So x equals 1, the opposite of b, plus or minus the square root of 1. 1 squared is 1, minus 4. AC is negative 4 over 2. Did y'all understand the application of the quadratic? You see it? Now we work on the inside. We get positive 16 added to 1. 17's prime. Nothing's going to simplify. So guess what? In proper form, to get full credit on big ideas and on my test, the zeros of that 4th degree polynomial are x equals. I prefer fractions, and they may also, but negative 0.5 is negative 1/2. 0.6 is 6/10, which is 3/5. And these guys. Four solutions, 4th degree polynomial, and in proper form. So the synthetic division skill is very necessary if you want your final results to be in quadratic form when it's necessary. But did you remember the first one we did with the cube? They all turned out very nice and pretty. It was a negative 1, a 4, and a 5. If that happens to you and your polynomial finder gives you all of them nice, rational, easy to write down things, then do it and move on to the next one. But if they turn out to be irrational, you've got to go through this process using the rational roots that your calculator gave you to depress it to a quadratic and then apply the quadratic formula. You see what you're up against? I hope. Okay. There you go. I don't think there was another one I had to show you. Oh, there was. What time do we get out of here? 10 after? I got one more thing to show you. Sorry. Ready for this last thing? Because on this last skill, example 5, then we're going to go backwards, and I need you to switch gears in your mind. We're not going to find the zeros. They're going to give us the zeros, and you're going to find the polynomial they belong to.
Oh, that's
So we're going to go backwards. We are going to be given the zeros, and you have to recover the polynomial that they are zeros with for. Okay, and watch these weird zeros we're going to get. We have a polynomial whose zeros are 3 and 2 plus root 5. now here's the part that you're going to stumble on unless you pay attention right now. If they give you an irrational zero, you can be absolutely certain that its conjugate is also a zero. Because in the quadratic formula, you always get 2 plus root 5 and 2 minus root 5. They always come together in pairs, right? So if they tell you that one of the zeros is 2 plus root 5, you have to know that there's another one they didn't list for you, and it is 2 minus root 5. This only has one because it's a nice rational number. But the irrational ones always come in what we call conjugate pairs because of the quadratic formula that produced them. Are you with me? Now, let me show you. I'm going to have to shortcut this a little bit. This is how we would begin to recover the quadratic. Before I do this one, if I had the zeros of 3, -2, and 1, do you understand that those came from factors that look like this?
Yes.
And that these came from a polynomial that requires you to multiply these? Multiply those together, you would get x cubed minus x squared minus x squared plus x minus 6x plus 6. Remember doing this at the beginning of the chapter? And you get x cubed minus 2x squared minus 5x plus 6. What I'm telling you is this function crosses the x-axis at these places. That's what we've recovered. Here's the zeros. Here's the factors they came from. Multiply them out the way you know how. Clean it up. Get the cubic function. This cubed polynomial starts low and ends high and crosses the x-axis at those 3 places. That's what we've discovered. It's the polynomial with these for zeros. Do you understand what we've discovered? If you try to do that with this over here, you would have these factors. X minus 3. And then, x minus 2 plus root 5 in parentheses because there's 2 terms, and x plus parenthesis 2 minus root 5. Close it. And then you would have to multiply these 2 together. I recommend you always do the conjugates together. Don't use this one last. And you would have a tough time doing that because the first thing you'd have to do is distribute the negative. That should be a negative. My mistake. There you go, Johnson. Okay. That's what you would have to do. And then you would multiply those 2 things together. You would get 9 terms that you would have to clean up as much as possible, and then take that times x minus 3. And there's an awful lot of opportunity for mistakes in this. I want to show you a better way. If you'll use it, you'll make far fewer mistakes and get this product way faster. This is also not in the book. I went to a week-long conference for teachers one time, and they showed me this at one of the meetings, and it was worth the entire week. Here it is. What you write is, if they give you these for zeros, they usually give it to you like this, x equals, right? So we're going to exploit this equation. It's going to be, I'm going to write this. I'm going to write x equals 2 plus or minus root 5. I'm going to write both of those irrational guys together in one equation. This, it also equals 3, and I'm going to get this out of it. That's easy. But what would this times this times this, what would that actually equal? I can show you how to get it much, much faster. Here's how you do it. Now watch. You bring the 2 over so that the ugly stuff, the plus minus, which is hard to deal with, and the radical stuff, that kind of junk, I call that the ugly stuff. I'm going to isolate the ugly. Again, we discriminate in this class. We don't like ugly things. Put them off to the side. Do you understand that little move?
Yep.
And then you square both sides because squaring fixes all ugliness. It does. You square this. Remember, you have to square a binomial. You have to remember this little fact. It's going to be x squared minus 4x plus 4. Do you remember that? And this is just 5. Why? Because when you square a positive, you get a positive. When you square a negative, you get a positive. And when you square a radical, you get what's underneath. Bring that over and you have your quadratic. That quadratic is what you would get if you multiplied this times this and cleaned it all up and didn't make any mistakes. That's 4 lines, yes, but this would take 1 line, but you'd have 9 terms that all need to be added together, and you You make mistakes when you multiply all these negatives and stuff. A lot of people forget how to distribute a negative like I just did. You make a mistake right there, you screw it up. This causes far fewer mistakes. So now, if you understand this little skill right here, what we have is this result. And I need to multiply that by this one to recover the formula. Okay? So we get x to the third minus 4x squared. You still have to do this, minus x. Most people don't mind doing this. It's just, it takes a while. And then you clean it up. That third degree polynomial has these three things for zeros. Okay, now that I showed you all this stuff, let me go through it in an accelerated way to show you what you're going to be up against when you see a problem like this. They are going to present it to you like this, possibly, or they might write 2 minus root 5. You have to know, as the doer of the problem, that if they give you one, an irrational one in this form, you have also put the conjugate. Then you write both of those together, x equals it. Isolate the ugly stuff, square both sides, bring it over. That quadratic times the one that this one belongs to gives you the polynomial. That was an accelerated version of what you do. You have to know what to add in. You take those two ugly things over here, x equals that, isolate the ugly, square both sides, and it gives you a quadratic that produced those that you now multiply by the linear that produced that one. Boil them together, get the cubic that produced them all. Does that make sense to you?
Yep.
You may want to take a picture of that, this along with that before you leave. Or go look at my video so you can see it. This trick is not in your book, but it's a great trick and it works every time. Okay? To find the quadratic that produced these uglies, this is the most efficient. Then you take that result times any linears that were nice until you produce the equation. Now, those of you doing it on paper, here's the assignment. Do the best you can. Bring me your questions Monday. We won't go on Monday. Here's the assignment. Are you ready? Is anybody doing this on paper? Okay, this first statement is going to be really weird to you. It's 3 through 19. Every other odd. So you're going to do 3 but not 5, 7 but not 9. You understand?
Yeah.
So EEO. 3 through 19 every other odd, then 25 to 39 odd. 40. 41 to 45 odd. 49. 50 D. 57 A, 66, 68, and 71. Now, those of you doing it on big ideas might want to make a note of this. The only thing even on big ideas that I require is the D part of 50 and the A part of 57. You may want to make a note of that because you won't be able to do the other parts. It will be really, really hard, and I don't require it. So on the D, on 50, 50, just do the D part. The D is in door. And on 57, just do the A part. And I will forgive you for not getting 90%. If that's what you do, because you'll miss those other parts. You need about 88%. You can forget those other parts on most problems. Okay? All right, if you're viewing this, we're all done. Bye. Have a good day.